Dijkstra's algorithm is the shortest path algorithm. So here I've made an app to demonstrate Dijkstra's algorithm. We've got black cells and white cells. Now the black cells represent walls that can't be crossed, and the white cells represent available spaces. I can click anywhere in this grid to mark a start position and click somewhere else, and it will run the Dijkstra algorithm to find the shortest path from the start to the end. And then I could just click start and end again. So that's Dijkstra in action. It's quite a simple algorithm to implement. So let me show you how it's done. Okay, so I've made this application where we can click the start and end positions. It's marking the green start position and the red end position. And when we click a new start, it clears off the old positions that were marked. And I'm going to implement Dijkstra in this application. So we'll quickly review the application, and I'll give you a link to where you can download this if you'd like to play with it. But let's have a review of the code so far. So what we have is a grid class, and that has a 2D array of grid cell values, and the grid cell values is a enum, and it can be one of these different elements. So invalid, that means that it's not, well, we don't actually put invalid in the grid, but what invalid means is it's a square outside the range of the grid. We'll see what we do with that shortly. An empty cell value is something that we can click on, a white square in our application. A rock is part of the black walls where we cannot go through them. Then we have our start position, our end position, and an element of the root, which is used after we've solved using Dijkstra. So we have a grid size. It's a square grid, so we have grid size cells across and down, and we have a start and an end position, and they are grid coordinates. Now if we take a look at what a grid coordinate is, that's just an X and a Y position. We can construct it and get the X and Y. We've actually got a method in here which is going to be used in Dijkstra, and that is get adjacent coordinates, and that takes the X and the Y position of this coordinate and it gives us the 4 adjacent coordinates, the one to the left, which is X minus 1, the one to the right, the one above it, and the one below it. We've got a hash code and an equals method and a standard 2-string method there. So that's grid coordinate. We initialize our grid, we remember the size, and we create our 2D array of grid cell values, which if you remember is the enum. And then we can get the grid, get the grid size. We could get the cell value at a grid coordinate, so that will just return the value out of the 2D array. If we go outside of the bounds of the arrays, which means we're asking for example a grid coordinate -1, so we've gone outside of the range of our grid, it will return a grid cell value invalid, and that's what the invalid flag is for. And we can set the cell values, so we give it the grid coordinate we want to set and the cell value that we want to set in the grid, and then we just set the value in the array. I'm also remembering if we are setting it to start or end, so I can quickly fetch start or end out of this class. And clear, I just loop through the array. I've got a X for loop and a Y for loop. I get the grid coordinate at X, Y, and if it is not a rock, I'm setting it to empty. If it is a rock, we want to keep it, so the rock is the pattern of walls. Then we have get start and get end. Now grid is an abstract class. The idea is that I can extend that, and I got the idea of this Hilbert Maze from the codility exercise. this is not my submission to that Codility exercise. This is just a video about Dijkstra, but here is a Hilbert Maze. So I've extended grid, and in this I'm calling set cell values, and this is actually an implementation of the Hilbert Maze. We take a pattern which is like this N shape, and we put it next to itself and connect it up, and then we rotate it clockwise and put it here, and rotate it anti-clockwise and put it there, and we connect all that together, and then we repeat that. So we take this whole pattern here, put it there, then we rotate it, and then we have that bit there, and then we repeat again, and we keep going recursively as much as we like to create a more complicated pattern. But I think that this level of complexity is suitable for this demo. So that's our implementation of Hilbert Maze. I'm not going to go into how that works, but you can see the pattern that it creates. And then we have a user interface class. So this is a JFrame. What's this doing? This has this cell size is the number of pixels we want to use for each cell. It has a phase, start and end, and we start off as in the start phase. So you have a grid button. They have an X and a Y position in the grid. They have an action listener. If the phase is let's look at the start phase. We call listener clear, and that will clear down the grid, and then we click the coordinate in listener with the grid cell value start, and we set the phase to end, and we update a status bar. If we click end, we select end, and we set the phase back to start and set a status bar. The refresh, what that's doing is it's looping through all the grids. If the value at grid coordinate for the X and Y of this button is empty, we're setting this cell white. If it's end position, we're setting it red. If it's start, it's green. If it's part of our route, we're setting it blue. And if we don't know, we shouldn't get there. But if we don't know, we'll set it to white. Then we have a grid listener. A grid listener is a class outside of this one that's listening to things that are happening, that we're calling from these buttons. And then we have a list of grid buttons. We have our grid. We have a panel to put our grid in, and a text area for our status bar. We're constructing the class here, and we're creating grid cells, which are these buttons, for each of our coordinates in our grid. If the grid is a rock, we're just setting a black label just as a placeholder that we can't click on. Then we're exiting if we close the window. The refresh button is going to call refresh on each grid button in the grid, and that is the method that was set in the color of the cell. And set status is just telling us whether we're going to start or end. Now if I look at the grid listener, that's an interface, and that gives us methods to click the grid or clear the grid. And then our main class, the Dijkstra class, that implements grid listener. That has our UI and our grid. It constructs our UI from our grid. It starts the whole thing off by saying we want to run Dijkstra with a Hilbert Maze, and the Hilbert Maze takes the size, the number of iterations we want to do in the pattern. And then we have the click method and the clear method. So the click method is going to set the cell value in the grid. If we are setting the end value, we'll call solve, and then we refresh the grid. Our clear, if we click clear, we will clear our grid and refresh our user interface. So that's the application we're going to use to implement Dijkstra. Okay, so the way Dijkstra works is we're going to give it a start and an end position, and let's say we just pick random start position. We'll put the start there, and we'll put an end position. We won't go too far, but we'll go to there. Now what we want to do is we want to start off by creating routes or paths, or whatever one we want to call it. We want to start off by creating a path in each direction away from the start position. So that's what the get adjacent cells method is going to do. It's going to give us the 4 cells around our current position. Now we're going to check those cells to see if they're available. In this case, this one here is available and this one here is available. The other 2 are going to be a rock. So we're going to get 2 paths out of this position. Then what we're going to do is sort those paths in the order of length. They're both just 1 step forward, so they're both the same length, and then we're going to work through them. Let's just say we look at this one next. We're going to get the cells around that. We don't want to revisit a cell, so we're not going to have anything to do here. So we're going to get the 4 cells out of get adjacent cells. We can't do that one because it's a rock. We can't do that one because it's a rock. We can't do that one because it's a rock, and we can't do that one because we visited it before. So we've finished with that path altogether. It's reached a dead end. Now we'll look at this path. We can go here to the left. We could go to the right. We can't go down because we visited it before. We can't go up because that's an invalid cell because it's outside of our range. So now we're going to have 2 paths. We're going to sort them. Look at the next one. We can go left there. Now the shortest path is going to be there, so we're going to go right there. Then we can go left and right, left and right. And now we're going to have a number of options. So we're going to have an extra path there and another one there. And here we're going to get to our destination. And because we're sorting our routes in between each iteration, we know we're going to hit, as soon as we hit the end cell, we know we've done it in the shortest possible way. So let's have a go at implementing that. Okay, so I've got my placeholder here for the solve method. I just need to implement the solve and then call it from here. Now, the first class I'm going to add is my Dijkstra path. So I'll just create the class. Now my Dijkstra path is going to be the route through. So what I'm going to do, I'm going to add a set of grid coordinates. And these are going to be our steps through the route. I'm going to make that a hash set, and the reason I want it to be a hash set is because I quickly want to be able to see whether it contains another grid coordinate. And I'm also going to remember the last grid coordinate because we're going to want to ask it. We'll call that last step. And I want to ask it quickly what was its last step. And we're going to want to construct this Dijkstra path with another Dijkstra path so that we can make copies of them. And we're also going to want to add a grid coordinate on the end. So when I've got a current path, I'm going to take a look at it. I'm going to extend it in different directions, and I'm going to create new Dijkstra paths from that original one. Now in the very first step, we'll just create it with a null path and just our start position. So I'm going to say if, I'll just fix that. I'll say if our other not null, then for grid coordinate other step in other steps, add the other step to this, and then add the step that we're adding here onto the end of it. So if we give it another path to initialize with, we're going to get all the steps from the other path and add it to the steps here, and then we're going to add our step onto the end. And remember the step that we just added. The next method I'm going to need, which is going to give us a list of grid coordinates, is a method to take a look at where we can go next. So get next available steps, and that I'm going to give this method the grid. I'm giving it the grid because it needs to look in the grid to see where we can go from the end of this path. So I'm going to get the adjacent coordinates by going from last step, get adjacent coordinates, and then I'm going to make a new list, next available steps, and that's going to loop through the candidate steps from the adjacent coordinates. And I'll say if this set of steps doesn't contain the candidate step, if it does contain the candidate step, we don't want to look at it because we visited it before. And then if grid get cell value of candidate step is empty, or grid get cell value is the end, which is our destination, then next available step add the candidate step. And finally, in this method, we return next available steps. So what that method is doing is, off the end of this Dijkstra path, it's going to give us all of the next places that we may want to visit. And then the final method we're going to need in here is just to return all our steps so that we can color in the grid at the end. Now, the other thing we're going to need this to do is to be sortable or comparable. So I'm going to say it implements comparable with another Dijkstra path, so that we can put these in a list and we can sort them. I'm going to add the compare to method, and that I want to test the step size minus the other step size. So we want to sort them in order of steps. Now sometimes in Dijkstra you may be that each step may have a different value. You may be looking at like a node with a node graph with paths connecting, and the paths may have different lengths, so that may be more complicated. But in this, each step has a value of 1, so we're just comparing the step size here with the step size in our other path. Now I'm going to create this solver class, Dijkstra solver. I'm going to give that the grid. I'm going to give it the start coordinate and the end coordinate. Save the grid. Get the start and end nodes from the grid, and then I'm going to create the solve method. Which is going to return the Dijkstra path, which is the one that gets us from the start to the end. I'll return null if we can't get there. So make a list of Dijkstra paths called candidates. And to this list, I'm going to add a Dijkstra path with just our start node in it. So I'm going to initialize it with null, no previous path, and just the start node. And then I'm going to say while not candidates is empty. Now in the past I've implemented Dijkstra as a recursive method, but I don't like it because the stack in Java isn't particularly large and you end up with a stack full exception. So I'm just going to implement this in a while loop, and I'm going to keep going until I have no more candidates to consider. And the first thing I'm going to do is sort our candidates. So I'm always going to look at the shortest candidate by saying Dijkstra path candidate that we're looking at now. It's the first candidate that I'm going to remove from the list. And then I'm going to say grid coordinate step in candidate get next available steps, taking the grid as a parameter. So for each step that we can do off the end of the path that we're looking at, which is the shortest path so far, Dijkstra path new path equals new Dijkstra path candidate, and we'll take that step. I keep spelling Dijkstra wrong. And then if the step is equal to the end, we've implemented the equals method in the grid coordinate there, and I'm going to return new path. Otherwise I'm going to add it to our candidates and then loop round again. If at any point we get to the end, we're going to return new path there. If we don't get to the end, we're going to return null. And then finally, I've just got the method solve to implement here. So I'm going to say Dijkstra path equals new Dijkstra solver for the grid, and solve call the solve method. And finally, if path is not null, then for each grid coordinate in path get steps. I'm going to set the cell value at the step coordinate to be grid cell value part of our route that will color the cell blue. And that's it. And then we can run that and click a start position, click an end position, and the Dijkstra will very quickly find the path, the shortest path from the start to the end. Now I've checked that code into Git, so if you'd like to have a play with it and make some improvements or see how it works, then here's the link where you can download that. Thanks for watching.